So we're looking at another example of independence where we have more than two events. With three events, say A, B, and C, independence means that any two are independent. So that would say probability of A and B is probability of A times probability of B, like that. Which might be called pairwise independence. And in addition, if you take all three of the events together, the probability A and B and C, all of them happening at the same time, is the product of these probabilities. And you can imagine, as we'll see in a minute, how you might think that that makes sense. We'll use this in the stoplight problem where I consider probabilities associated with traveling through three independently behaving traffic lights. So here, I got this great schematic. I got three lights. I'm taking my Maserati to work. I guess it looks like whatever that is. Maybe that's a Miata. It looks more like a Miata convertible. I don't know. Pretty tiny though. It could be anything. And then as you reach these lights, as you come to work, as you go through each of these lights, oh, that's why I'm late for work. Ha ha. Okay. The chance of hitting this light at a red and having to stop is 0.2. The chance of hitting this light at a red, which is and stopping, which is 0.1. The chance of hitting a red here and stopping is 0.4. And we're assuming that lights behave independently. That is to say, if I get stopped here, my chance of getting stopped there is still 0.1. If I get to travel through this light because it's not red, my chance of getting stopped there is still 0.1. Now, if you've done a lot of driving where there's a sequence of lights like that, the traffic engineers have tried to find a way to keep the traffic moving smoothly. And sometimes what that means is making it through this light causes you to stop here, so you don't all stack up at the third light. So I've seen that happen, where I make it through this light, but then I can never make it through the next light, and I get through that one. I can't really make it through that one either. Maybe it depends on the time of day, but even though there's no cars, you would think just once you're green here, you should just go green straight across. But I have the feeling once, if there's a lot of traffic in place, and you let that happen, when eventually the traffic stops, all of it gets stopped there, and it backs the traffic up way back across all these lights. So they want to make sure that you get slowed down once in a while to keep traffic flowing smoothly. So in that case, they're timing the lights against each other, and which means the lights aren't behaving independently. And then you can figure out what the rule is, and then you can decide how to drive. The way to fix the rule that seems to be happening around here is to just drive really fast from this light to this light so you can make it through while it's still green, otherwise you get stopped. And that's encouraging people to speed, so that's a danger that you run into if you're a traffic engineer and you set things up for traffic flow to be smooth as opposed to fast, maybe, and then people figure out if they drive fast they can make it through the lights, otherwise they can't, so everybody speeds. That could be happening. It could just be anecdotal evidence. It's just it looks like that's what's happening. And that's what's happening, and really there's no planning, but I think there is. So we're going to assume those lights behave independently, which says the probability of, say, stop, stop, stop would be red, red, red. And those probabilities separately look like this, but for them to happen together, we would multiply them together. So it'd be 0.2 times 0.1 times 0.4, like that. And that's not going to fit here, so I'm going to go ahead and figure out what it is in a minute, and then over here we're going to put the number of stops that were associated with that particular event. Number of stops, because I'm going to be worried about the probability distribution of the number of stops. The number of stops is 3 here, and this number here, it's got decimals in it. It's something with it's got an 8 in it, but is it 008? I think it is. 0.1 times 0.2 times 0.4, like that. 008. I guess I put it like this. I don't know about the colors. And then we've got stop, stop, go. 0.2, 0.1, 0.6. And that's got to be a little bit larger than that one, so I'm thinking that's 12, but it's 0012, 0.012, like that. That's 2 stops. And then stop, go, stop. Stop is 0.2. Now go for the second light is 0.9, and stop is 0.4. Like that. So that's 0.36 times 0.2 It's got to be 0.072. Let me double check it though. 0.2 times 0.9 times 0.4. What again? 0.2 times 0.9 times 0.4. 0.72. Go figure. And then stop, go, go is 0.2, 0.9, 0.6. So go, go is not stopping. So 1 minus that, 1 minus that. That makes sense? 0.2 times 0.9 times 0.6, like that. 0.108. We'll check these sum to 1 at the end of the day. Go, stop, stop. It's 0.8, 0.1, 0.4. I guess all these things look like they're 3 points deep. That makes sense because it's in scientific notation, 10 to the minus 1, 10 to the minus 1, 10 to the minus 1 for those. So you get 10 to the minus 3 times some number, and that's going to give us the third place over here. So this has to be 0.03. That's 32 is the number, but 0.032. I'm going to go with that, and I'll check they sum to 1 in a minute. Go, stop, go. 0.8, 0.1, 0.6. So that's 24. So 0 to, oh sorry, that's 48. So 0.48. Go, go, stop. 0.8. Oops, keep my color scheme correct. Go, go. 0.8, 0.9. Stop. 0.4. Oh, that's too much for me. Okay, so 0.8 times 0.9 times 0.4. 0.288. We'll know in a minute. Go, go, go. 0.8 times 0.9 times 0.6. 0.432. Go, go, go. 0.8, 0.9, 0.6. Okay, and then the double check on this. 0.008 plus 0.012 plus 0.072 plus 0.108 plus 0.032 plus 0.048 plus 0.288 plus 0.432. Enter. 1. Oh, I'm so excited. The sum is 1, you know, because I would have to just start over, go back to my desk, figure out what went wrong, and take a Valium and come back, I guess. So I'm going to put the number of stops here. 2, 1, 2, counting stops. 1, 1, 0, like that. All right, so now I can fill in the probability. So what you might care about, right, if you're coming to work, I don't want to stop at all. The chance of no stops is this 0.432. It only happens one way. You make it through all the lights. The chance of 3 stops, you stop at every light, I hate that, is pretty small, 0.008. There's only one way that happens, like that. And then for 2 stops, there's a bunch of different ways you can stop. The 3 different pairs of lights you might choose to stop at. The first 2, the second 2, the first and last. That's the 3 ways you could stop twice. And the probabilities are these values, 0.12, 0.72, and 0.32. So I'm going to add those probabilities together, because these are disjoint events. Stop, stop, go, and stop, go, stop. They're you can't do them both at the same time. That you make it through one way or the other way, but you can't do it both at the same time. So 0.12, we add to that 0.72, and then I can't see it, and then we add to that 0.032. So I get 116. So let me write what we did. 0.012, that's that one. 0.072 and 0.032 is equal to 0.116, like that. So that's these probabilities associated with 2. And then we'll add up the probabilities associated with 1 stop. So that's 0.108 and 0.048 and the glorious 0.288. So 2 goes, which is likely to happen, and stopping. Which is likely to happen too for that last light. So this whole process is likely to happen. And we'll add them up. 0.108 plus 0.048 plus 0.288. Double checking things. 0.444. So there we go. So good, almost 88% of the time, I stop not at all or just once. A pretty small percent of the time, I stop 2 or more times. Right around 12%, 12.5 maybe, something like that. That's a pretty small number. So it's all good. You don't get frustrated driving to work. If you don't have to stop very often, if you do stop, it's only once, mostly, not 2 or 3 times. A really low chance of all 3. And that's assuming independence. I don't think the lights are independent, so the situation's maybe worse than that. But that, I think that takes care of our introduction to independence, section 5.3. And then we'll move on to the next section coming up. Here we go.